In this video, I'd like to provide an introduction to Fourier series. So consider this graph of a function f of x that I've provided here, and let's think about some questions related to Taylor series. So if I were to ask you to find the Taylor series for this function f of x centered at x equals pi over 2, well, first of all, note that we could find pi over 2 on the graph, or the x value here. So this would be pi over 2. So we'd be looking at the graph near here. So in this case, if I want to find the Taylor series of f of x at pi over 2, essentially I'm looking at the graph of y equals pi over 2, because for values of x near pi over 2, that's the constant function it's equal to. In particular, if I were to plug in f of, let's see, if I plug in pi over 2, notice from the graph that we would get pi over 2. But for any derivative I would take of this particular function at pi over 2, I'm going to get 0 because I'm looking at a constant function on that piece of the graph. So as a result, the Taylor series would be then just equal to the constant function pi over 2. So maybe I'll write this. The Taylor series would be y equals pi over 2. So if I were to think about the graph of y equals pi over 2, notice that it would actually be a perfect fit for the function as long as x is between, say, 0 and pi. But as soon as I deviate from that interval, then it's not a great approximation of f, because the function then becomes minus pi over 2, but my Taylor series remains the constant function y equals pi over 2. Likewise, if I were then to ask for the Taylor series centered at minus pi over 2, a very similar behavior is going to occur. If we evaluate the function at minus pi over 2, we get the constant minus pi over 2, and any derivative we choose to take here is going to be 0, and certainly then it would be 0 when we evaluate it at pi over 2. So the Taylor series, if we just shift over a little bit, is likewise a constant function, but it's a very different constant function. So here we would get minus pi over 2, and this would be a good fit for my function. We see between, say, minus pi and 0, but not outside of that. And so one of the things to notice about this is that because when we're talking about Taylor series, we mention a center, there's some notion of a location on the x-axis that plays an important role. And in particular, unless the interval of convergence is the whole real line, we very much focus on the center and where around that we may get convergence of our series. For that reason, often we think of Taylor series as what we call local approximations, right? They give us good information, hopefully for some sizable interval around the center, and maybe not the whole real line unless the interval is the whole real line. So when we start to talk about Fourier series, which we will in a moment, those are by comparison what we think of as global approximations. You'll note that they don't have any center, and in general, when we start to look at graphs of these and later the convergence theorem, we'll see that we can actually get convergence for almost all points, and that's going to be something that's a really nice feature of Fourier series. The other problem with Taylor series that we can encounter is, what if I asked you to find the Taylor series of this function at x equals 0? What I'll point out is that this is not possible, because one of the things that needs to be true in order to find a Taylor series that we've kind of taken for granted in all of our examples so far is that you have to be able to find derivatives of the function at the center. This function I can see is defined to be pi over 2 at the center, but as soon as, if the center is 0, but as soon as I start to take derivatives, this function is not differentiable at 0. So one big fallback here we see then from Taylor series is I can't even find a Taylor series unless the function actually has infinitely many derivatives at the center. So the goal here is just to kind of point out Taylor series are great. We have seen a lot of really helpful things that we can do with them. But I do need to point out that there are functions for which we can't even find a Taylor series. And it also has this limiting constraint here of needing to have an interval of convergence, and possibly that can be very restrictive. So this leads us to now another way to approximate a function. And in particular, Fourier series, we're going to look at trying to approximate 2π periodic functions. You can actually use Fourier series to approximate any kind of periodic function, but in this course, we're just going to focus on 2π for now. And let's make sure that the concept of a periodic function is clear. A lot of times I think we associate that strictly with, say, trig functions. But here we're going to define a function that is k periodic if f of x plus k is equal to f of x for all k. And in terms of the wording there, we can say that f of x is k periodic, or we might instead say f of x has period k. Those things are equivalent. So if you think about the example we graphed above, that function is 2π periodic. So thinking about the definition, that would mean that, so let's go down at that here, that if I take f of 0 and think of that as my x value, f of 0 plus 2π should equal f of 0. Likewise, f of 4π should equal f of 2π, and therefore equal f of 0. And this kind of extends. And so I'm just using 0 as kind of a starting point. So not only can I use the fact that it's 2π periodic to set f of 0 and f of 2π equal to one another, you can really extend this idea and say that if I find an x value that is a whole number times 2π away from 0, then the function should evaluate to the same thing there as it does at 0. So that's kind of extending this idea of having period 2π. The goal that we're going to have with regard to Fourier series is that we want to take an arbitrary periodic function, and like I said, we'll focus on 2π periodic functions, and we want to approximate it using sines and cosines. An underlying fact that we're going to just take for granted is that we can take 2π periodic functions and write them as a sum of sines and cosines. So again, aligning this with Taylor series. And with Taylor series, we were trying to approximate a function by sums of powers of x. And here, we're looking at sums of sines and cosines toward that same goal. And we are restricting our focus to periodic functions, 2π periodic functions right now. So the last thing I'll put in this video is our definition of the Fourier series for a function f of x that's 2π periodic. So the series is going to be what I've boxed here, a constant term a sub 0 plus a sum of cosine terms with terms a sub k times cosine of kx, and plus another sum b sub k sine of kx. One thing to think about that might be confusing is notice that these do start at k equals 1, and with Taylor series, we've always been kind of focused on that index starting at 0. To remember, in some sense, why this is true, first of all, notice that if we started the last sum here at 0, because sine of 0 is 0, that would really just be irrelevant to put in a b sub 0 in there, because we would be multiplying it by 0. If I had k equals 0 in this cosine sum, cosine of 0 is 1, so that would just be a constant. But we've kind of separated that out over here. So that's one way to think about why we're starting this at 1, just to be careful with that. And then what I need to define here is how we find the coefficients, a sub 0, a sub k, and b sub k. Later, I'm going to talk about where these formulas come from, but at this point, I just want to write these down, and we're going to use that in another video to find a Fourier series. So here are my formulas, and a couple things to notice. The a sub 0 is the only one that has this multiplier of 1 over 2π, and a sub k and b sub k have only a multiplier of 1 over pi. To find the ak and bk, remember that we're going to integrate the function f of x multiplied by the very same function that a sub k or b sub k serves as a coefficient for. So with this, we're going to, in another video, really go through in detail how one could find the Fourier series for a particular f of x. And again, I'll point out that for the definition here, some of these things are just going to be fixed for all of our Fourier series. The key thing that's going to change as I get a different 2 pi periodic function is just what we plug in for these pink boxes. The rest of this formula is standard. And this is much like when we did Taylor series. We had a definition, and we had to find the kth derivatives of f at the center, and that's what we plugged into our kind of standard definition. The rest of it, the k factorial in the denominator, the x minus a to the k, that always came with it. So as we get new examples, really the bulk of the work comes with computing these integrals so we know what those coefficients are for our particular f of x.